All right, everybody. Welcome back. Hope you're all doing well. I'm going to talk about pH scales today. So I'm going to start with a little visual. Right there is a pH scale. You've probably seen something similar to that before. But if you look at the screen there, in the middle, neutral is what it's labeled, is pure water at pH 7. And don't worry about the colors. They don't really mean anything there. It's just to show a contrast from the different sides. But on the left side, on the acidic side, hopefully it's left to you. They didn't flip it around. But you have things like soda, vinegar, lemon juice, and battery acid that's more and more acidic as you get lower and lower numbers. And then on the other side of neutral, the basic side or alkaline side, you've got things like ammonia and bleach as you get more basic. That's kind of an idea of what we're talking about today. Where does all that come from? Let's take a look. Let's go into here. Yep, that looks good. All right, there's also a couple of videos. There's a video here linked, and I think there's a different video on the actual website that you can click on and watch. It gives you a little more background on the whole pH scale and why you'd use a logarithmic function, a scale that has a logarithmic function for this kind of thing. I'm not going to talk a lot about it. You can watch those if you want. All right, so here's the idea. You have solutions, and they're basically going to fall into one of these three categories. It's going to either be acidic, basic, or neutral. And the way that we measure is the scale, or whether we very quickly categorize things is using this scale, and that helps us compare a pH scale. It goes from sort of 0 through 14. It actually goes below 0 and a little bit higher than 14, but that's beyond our class, so ignore that. But anyway, if you have an acidic solution, it simply means you have a higher concentration of H plus ions compared to hydroxide ions. And I try to show a little visual here of the larger H plus ions greater than hydroxide ion concentration when you have an acidic solution. If it is basic, however, it's the flip side. You have a smaller concentration of H plus ions compared to hydroxide ions. If, however, you have a neutral solution, it doesn't mean that you don't have these ions. It just means that you have both ions in equal concentrations. So that's a neutral solution. Both ions are present, just in exactly the same amounts. All right, let's keep going. So here's the equation that we're going to use to solve for pH. And it's on your reference sheet. If we were to ever have a quiz or a test, then it's there at your disposal and you don't have to memorize it. But it's simple, and hopefully you've had logarithmic functions, regardless of the base. The easiest base to deal with for logs is 10. So that's what we're using here. But pH is simply the negative log, base 10, of the H plus ion concentration. And when you take a log base 10 of a really small number, unfortunately, it becomes a negative number. So that's why the negative is there, is to get rid of the negative once you do the math. All that to say, though, when you have a lower pH, it's really just indicative of a larger concentration of H plus ions. But when we say larger, it's still really small. So that's kind of the problem. And we had an interesting discussion in AP Chemistry this year in the kind of shortcomings of this scale, and if we could figure out a better scale that we could have used. It's too late now. We're stuck with this scale. Everybody uses it. Anyways, but yeah, low pH does go hand in hand with having an acidic solution. A high pH, on the other hand, means you have a smaller concentration of H plus ions. And as a result, because this is a give and take, the smaller the H plus ion concentration, the larger hydroxide ion concentration. And this would be, again, this goes along with a basic solution or an alkaline solution. One thing to note is water. When you have a solution, your solution's in water, right? So you have all these water molecules bouncing around. And the reality is water, not all of water is water molecules. Some of the water molecules basically break into ions. They self-ionize. It's a small amount, but nevertheless, it's present. And from those ions, that's where all the scale comes in, because that's where we can compare the H plus to the OH minus concentration. So, for example, if you had pure water, a small percentage breaks into ions, and you see right there the data for pure water, H plus ion. This is at 25 degrees Celsius, so basically room temperature. But you end up with 1 times 10 to the negative 7 molarity concentration of H plus ions. And it's the exact same concentration of hydroxide ions, because every water molecule, when it breaks apart, it breaks into equal amounts of H plus and OH minus ions. So they're going to be, as long as it's just water, you're going to have equal concentrations of both of those ions. All right, so we talk about water being neutral because it does indeed have the equal amounts of H plus compared to OH minus ions. Again, it's because each water molecule, when it splits up, you get one of each. And when you do the math, I'll do the math in a little bit, but when you do the math to figure out what's the pH of this neutral solution, all you need is the H plus ion concentration, and here it is right here. You punch it in the calculator, you get 7. That's the pH of neutral solutions. Again, at normal temperatures, like 25 Celsius. All right, let's talk about where this whole, I already kind of did, but the pH, it is a logarithmic function, and the reason for that, and if you watch the videos, then this would be obvious, but the reason for it is pure water, as you just saw, it was just written here. I'll rewrite it though. It was 1 times 10 to the negative 7. I'll write it out fully though, 0.000001. That's the concentration of H plus ions for pure water. And it would be the exact same concentration for hydroxide ions, but we're just comparing H plus right now. If you look at this acid right here, hydrochloric acid, this is 0.1 molar. It's not very strong in terms of concentration, but that's an acid we've used several times in lab this year. How does that compare? The concentration is 0.1. Let's get it on the same line for you there. 0.1. So we had 0.0000001 molarity compared to 0.1 molarity. It's a huge difference. And because of that huge difference, somebody was just hurting for a different way to compare it. And so we came up with this pH scale, used log base 10. So if you take the negative log of that H plus ion, you get 7 for the pure water. And it is, it's 1. If you take the negative log of 0.1, it's 1 for the hydrochloric acid. So now we just have to compare 7 and 1 instead of 0.0000001. You get the idea. Okay, that's why the scale is what it is. But understand, and this would be a question, that the pH scale, just like the Richter scale, every number on this scale differs by a factor of 10. So if you have two acids, one's pH 2 and one's pH 4, they're both acidic. But the pH 2 isn't just like a little bit more acidic than pH 4. No, it's 100 times stronger than the pH 4 acid. In other words, it's 100 times the concentration of H plus ions compared to the pH 4 solution. So it's a big deal. Every little bit on the pH scale is a big deal. All right, let's talk math before my kids go crazy in the background. If you're trying to find the pH, you already saw the equation. pH is simply the negative log of the H plus ion concentration. So all you need is the H plus ion concentration. So here's an example. If you know the H plus ion concentration of some solution was 1 times 10, 1.0 times 10 to the negative 5 molarity, all you got to do is take the negative log of that. I will try that right now. Hopefully it works. Oop, let's get rid of that. I can't move this, so I just covered up some stuff. But I will type in, on your calculators, you're probably going to type in as you read it, negative, then log, and then the concentration. But on this calculator, I kind of have to work backwards. I type in the concentration 1.0 EE, so times 10 to the negative 5. Uh-oh. I got to take the negative. Let's try that again. 1.0 EE negative 5. There we go. Here, that's what it looks like. Take the log of that and take the negative of that. Somehow I screwed that up. One more time. 1.0 exponent negative 5. There's the number. Take the log negative of it. That's 5. So that's what the answer would say right here, but it's obscured by the calculator. So why don't you try one? Try this example one right now. Pause the video. What is the pH of this solution that has a H plus ion concentration of 5.6 times 10 to the negative 10 molarity? Okay, you're back. You figured it out. Great. I'm glad you paused that video. So let me type it in and we'll see if your answer matches mine. Again, I have to work backwards. Type in the concentration first. Negative 10. That's what it looks like. Take the log negative of it. 9.25 is my pH. So let's write that, 9.25. Did you get that same answer? You did? Awesome. Good job. All right, let's talk some more. POH, what's that, you ask? Well, remember there was H plus and there's OH minus, and we previously with the pH scale just focus on the H plus. Well, that's not fair to the hydroxide ions, is it? We could also focus on the hydroxide, and we have a POH. POH, the math is very, very similar. It's the negative log of the concentration. That's how you find POH, but in this case, we're finding the negative log of the concentration of OH minus ions, as you kind of guess. It gets better though. There's additional math. Since it is a give and take, as H plus ions increases, OH minus ions have to decrease and vice versa. The math works out where pH plus POH is equal to 14 at 25 Celsius at room temperature. So you can do some really simple math. If you know the pH of a solution is 4.6, then you take your little calculator, you go 14 minus 4.6 will tell me my POH is 9.4. Great. So that's really easy. Easy way to go from pH to POH and vice versa. They have to add up to 14. What else? Here's where let's talk about going the opposite direction. You're not solving for the pH, you know the pH, and you're trying to solve for the concentration of H plus ions. This is usually where students find a little bit more difficulty because I think, well, never mind, I'm not going to speculate. But the equation is still valid. pH is equal to negative log of H plus ion concentrations. You're just going to, and if we were in class, I would do this on a board, but we're not, and I can't write, so I'm just going to tell you, if you rearrange that equation using correct math skills, you get this right here. H plus ion concentration is simply equal 10 to the exponent of your negative pH, right? Which basically means you're going to use the 10 to the x button on your calculator. It's very often the same exact button as the log, just a second function of that. So I don't have that button on my calculator here on the computer screen, but I'll show you nevertheless. If you have any solution that has a pH of 2.10 and you're like, all right, great, what's the H plus ion concentration? Here's how you do it. You would use the 10x button, which I don't have, so I'm going to manufacture it by saying 10 y to the x. So that's my 10x button, essentially. Now all I have to type in, it's waiting for me to type in my exponent, and I got to type in the negative pH. What was the pH? Ooh, it was 2.10, so negative 2.10. What do I get? 0.00794. Okay, I'm going to say two significant figures for now, 0.0079. Now this is a concentration, it's a molarity concentration, so I need to put on the units for molarity. The pH does not have units because it is just somebody's mathematical construct. It's not really representing anything. We took a real thing like molarity concentration, and we did some maths to it just because we felt like it. So there's no units to the pH or the POH. But concentrations do have units, so make sure you don't screw that part up. It's a very common error. Great, so it's 0.0079 molarity. Why did I stop with two significant figures? There's another thing I should tell you. pH scale and the POH scale, and if you understand the math, this actually makes a lot of sense. But for pH and POH, it's not like normal significant figures. You actually only count after the decimal place. Those are the significant figures. It doesn't matter if there's a 2 in front or a 10. Those numbers don't matter. It's only after the decimal. So 10 is two significant figures, hence the reason why I needed two significant figures on my concentration. So 0.0079. All right, so still working with the same solution. What can I say about the POH of the same solution? Well, remember, They have to add up to 14, pH and POH. So you could probably do this in your head, but I'm going to use a calculator just for giggles. 14 minus 2.10, 11.9, but I know that I need two significant figures, so 90. What about the OH minus concentration? How do I figure that out? Well, just like we did here, the 10 to the x of the negative POH will tell me my OH minus concentration. So let's try that. Come on. Start off with 10 to the x button. And then I'm going to put in this exponent of negative 11.90. What does it say? Ooh, it's a really small number. 1 point, let's do two significant figures. 1 point, that's going to round up to 3. So 1.3 times 10 to the negative 12. 1.3, I'll just write it e to the negative 12. And again, this is a concentration, so I need my units molarity. Boom, easy as pie, right? There's also additional math. I could have solved for hydroxide ion concentrations a different way too, because there's a second mathematical relationship, but it's on your reference sheet as well. H plus ions times hydroxide ion concentration will always equal, that product will always be 1 times 10 to the negative 14 at 25 Celsius. Again, that's why it says at normal temperatures. You change the temperature, things get a little bit off with the numbers. So we're not going to. We're sticking with 25 Celsius. You're welcome. Anyway, if you want, here, I'll prove it to you. Watch this. If we knew they had to add up, or sorry, they had to multiply together to form 1.0 to the exponent of negative 14, like that. And I knew the H plus ion was 0.0079. I'm going to divide 0.0079 on both sides, so 0.0079. So, whoa, look at that. Round that off to two significant figures, 1.3 times 10 to the negative 12. I could have figured that out a different way. Crazy, but true. All right. Hopefully that makes sense. If you have any questions, feel free to remind text or email me. What I've already mentioned, but it's listed right here in the bottom, there's no units for pH and POH, right? Those are we just made up those scales just to make things easier to compare. But concentrations do have units. Make sure you have the units, molarity units on those. And I just mentioned about the significant figures. It's a little bit hard for some people to grasp at first, but do the best you can. Alrighty. You can now answer all those questions on pH. Good luck. See ya. Oops.